everyone, I am starting a new lecture video for Chapter 8. We're going to be going over sampling distributions, and this is using the updated lecture notes from fall 2020. So that's what we will be looking at for this. So let's go to those notes. Now, one thing about Chapter 8 that's good is that it is very similar to Chapter 7 because we'll still be talking about the normal distribution, and so we'll still be using the same functions in our calculator. The main thing that's going to change is what numbers we are typing into the calculator. So Chapter 8 is all about sampling distributions. So first we kind of have to understand what a sampling distribution is. So we've got two sections in this chapter. The first section we're going to be looking at the distribution of sample means, which remember a sample mean of course is x bar, right? So we'll be dealing with x bar in this first part. And the second section we're going to be looking at proportions, which we'll call p hat. So we looked at in Chapter 1 something called sampling error, and sampling error is the error that comes because we use a sample to estimate a population characteristic. This is something that's going to happen in every sample because unfortunately we're never going to have the perfect sample. So every sample is going to give us a little bit different result. If you want to think about like maybe election polls right now, every poll, even if they're taking a similar sample size from the similar population, you'll notice that you get different percentages, right? And hopefully all those percentages are similar to each other, but we will still see that they're going to be different. So if you get a poll that says 43% is going to vote for candidate A, and then you see another poll that says 45%, and another poll says 40%, and you're wondering, well, they can't all be right, so which one is right, or are they all wrong? And honestly, most of the time, most polls are going to be wrong in some way. It's just how wrong are they, right? So we want them to be as close as possible, but we do have to be aware of sampling error. And so that's something that's really important in this chapter, and then also going forward with how we interpret our results in a statistical test. So let's just do a quick example identifying population and sample like we would have in Chapter 1. So in this example, where we're taking a sample of 50 students, the population, we would say, would be all students at this community college, right? The sample would be the 50 students that we actually got information from, and we were wanting to know about scholarship money. Okay, so scholarship money is what we're looking for. And so we got in our sample, 275 was the average amount given. And so this would be a sample mean, right? Because it came from sample. So because it's a sample mean, it would be labeled as X bar, right? Instead of being labeled as mu. So should we expect the mean scholarship money from the sample to be exactly equal to the mean scholarship money of all the community college students? Probably not. Of course, we would like it to be, right? We would hope that it's going to be pretty close, but it probably won't be exactly equal, okay? So thinking about that concept of sampling error, what we're going to be looking at with sampling distributions is we're going to have some population. So let's say this is our population, and this is scholarship money. Sorry, my writing's not as good on this. this writing tablet that I've got. But so let's say this population is scholarship money, okay? And so there's some true mean, some true average scholarship money that we have among the population. And inside here, these would be all the different students and the scholarship money that they got, right? So you'd have some over here, some up in here, and then you kind of have this average where most students are somewhere here, and then some have a little less and some have a little more. Now, if we're taking samples from here, what we would see is we'd be taking, let's say, a sample of, let's see, what did we do on that last one? Already forgot. 50, right? So let's say we're taking samples of 50. And for that first sample, we got a sample mean of 275. There we go. So we got a sample mean of 275. So then we might take another sample, right? And that sample, let's say we're still going to take a sample of 50. Okay, and then we find the sample mean, and it comes out to 260. All right, so we could continue doing this and taking different samples, but as we take samples, let's say we are sticking with the sample size of 50. If we were to take every possible sample from this original population, what we're going to create is our sampling distribution, okay? And so the sampling distribution here is a new distribution that has all the sample means that could be calculated from samples of size 50. Okay, so in chapter 7, this is what we were working with, was the original population. Okay, in chapter 8, we're going to be looking at this, where now we're looking at, instead of just one person, like we might have said in chapter 7, what's the probability a student will get, $290 in scholarship money or more. Maybe we're trying to find that. But in this chapter, we'll be looking at what's the probability that a group of 50 students would have a scholarship money average of 280 or more. Okay, so the main difference that we'll see in these problems is that instead of just looking at one person at a time, we are looking at a group. And so then that would take us to wondering, well, what would the sampling distribution look like? If I am taking all these different samples here and putting them into this sampling distribution, how do I know that it's going to look normal, or is it going to look normal? Okay, so let's look at this example. So this would kind of be like a quality control type problem. We've got 12-ounce soda cans that we're producing at this soft drink company. They have a mean of 12.19 ounces and a standard deviation of 0.11. Now, it says the chart below. We're not going to have that anymore because we're not really going to be working on this together. But let's say we're going to take simple random samples of size 10 and find the sample mean for each. So what we would do here is we would go to that population, okay, this population of soda cans, and we're taking different samples of size 10 and calculating their average. So one way we can look at how sampling distributions act is by using a tool. This one I'm going to be using is STA220, but there's lots of different calculators that'll show you kind of how a sampling distribution works. And so what I've got here is it's one of the applets that you can choose here in STA220. But so our distribution is going to be, sorry, get this. It is going to be bell-shaped, okay, and it said we had a mean of 12.19. And our standard deviation is 0.11. All right, so what this does for us is it is going to show us what happens when we take different samples. So instead of us having to, well, let me change that. It looks a little weird like that. Okay, instead of us having to calculate averages and all that, we're just going to look at what would actually be going on if we took those different samples. All right, so we're going to do samples of size 10. We will talk about later on, what sample size we want to do and all that, but for now we're just using 10 because that's what the problem said. All right, so here's our original population. So what we're going to do is we're going to take a sample of size 10, and so what this is going to show us is the different values that are being chosen. Okay, so since we're taking samples of size 10, you can see that these are all just randomly being chosen. Okay, so we got one over here and here and here. But what we would think of is, because most of our data is somewhere in the middle here, we would expect most of the values that we randomly choose are going to be somewhere here, right? Now, it's obviously possible that we could get values way over here or over here, but it's much more likely to get values here. So once it's done looking at all 10 of these, then it's going to calculate the average. Okay, so it randomly chose 10 different values from the population, and then this down here is our sample mean. Okay, so the sample mean is 0.173. All right, so that would be our first one. We could go back and do it again. Okay, so it would pull another one. And so what this does is it does show us what each of those values are that are being chosen. And then it also kind of keeps up with what are the averages every time. Now, obviously, it's running slow because I guess my internet is just being overextended right now. So normally this goes fairly quickly when it's choosing it. So if you wanted to do some of these on your own, you can. You can go to StatCrunch and just choose the applets and go to the sampling distribution one. But so this next one we got was 12.2079. Okay, and then you would just keep going, right? And so if we did every possible one from here, if we took every possible sample of size 10, then those would all live down here. Okay, we would take every possible sample of size 10, calculate the sample mean, and that would create this new distribution, which is what we're calling the sampling distribution. So for example, up here, we could do 1,000 samples of size 10, okay? And this one, it doesn't do one at a time, thankfully. So it's not going to show you all 1,000 times that it creates a sample of size 10. But what we do see is we see how we create this new distribution of all sample means from samples of size 10. And we could do it again and again and again. And the more we do it, what you should notice is that that green curve down here is becoming more and more normal, right? So notice how now it's basically exactly normal at this point. We've taken about 8,000 samples, which is a lot, right? And notice what's happened to the mean. It's 12.19. So this is the mean of the means. Okay, so this is the average of all the averages. And what we're going to notice is that this mean is the same as the original population mean, right? And that's not something that just happens to happen on this one. It will happen for every distribution. And another thing we'll notice is this green curve is much more narrow than this one, right? The gray curve up here has a standard deviation of 0.1, okay, and that describes how spread out the data is going to be. But the curve has a standard deviation of 0.0351. So much less than the original population. And that is something else that's also always going to happen in our sampling distributions. We're going to have the same mean as the original population, but our standard deviation is going to decrease because we're much less likely to get averages that are way over here or way over here, right? Because these are individual items, right? But once we choose 10 different individual items, those 10 items are averaged and much more likely to get a value somewhere here in the middle, right? It'd be very unusual to get an average of 10 values from this population that gave us numbers, way out here, way over here, because there's just not enough individual values that could create a sample mean that would be that extreme. So we are going to see our standard deviation be smaller. That last screen in the sampling distribution applet was that if we're looking at comparing, one soda can to another soda can versus the average weight of 10 cans to the average weight of another 10 soda cans, these should be more similar, right? These should be more similar. Whereas these here, if we're just picking individual cans, it's possible you could get one that was really low and one that was really high, or you could get two that are right in the middle, right? But it's more likely to get similar sample means than it is to get similar X values, okay, which should be our individual values. So describing the distribution of sample means, we could see from our example that we looked at through StatCrunch that when we took every possible sample of size 10, or at least we took a lot of those samples, right? We did 8,000 different samples, that the new distribution seemed to be more narrow than the original, but the mean seemed to still be at the same mean as the original population, right? But the standard deviation was definitely lower for that sampling distribution. So let's see the actual mathematical definition of how we're going to define the mean and the standard deviation. Okay, so for the sampling distribution of the sample mean, we are going to have a mean that's equal to mu, so that's the mean from the original population, and the standard deviation of this new distribution is going to be equal to sigma over the square root of n. This is also sometimes called the standard error instead of being called the standard deviation, but either way, it's the same thing. Now, I will have a little bit new notation because, we're going to be talking about the original population. Okay, so the original population has a mu and a sigma. Now, the sampling distribution, of course, also has a mean and a standard deviation, right? So we don't want to label them both the same thing. It'll be confusing. So the sampling distribution for x bar, we're going to use mu sub x bar. So we'll have the mean with a little x bar in the subscript, and then sigma sub x bar. And so then that'll let us know if we're talking about the original population or the sampling distribution. So you can kind of see that done down here when we're calculating the standard deviation of the sampling distribution. It would be sigma sub x bar, and that's going to be equal to sigma over the square root of n. So depending on what your sample size is here, that is going to change what your sampling distribution standard deviation is, right? So as we increase our sample size here, we're going to notice that our standard deviation of the sampling distribution here is going to decrease. So as we increase sample size, we're going to get a smaller and smaller standard error. And that is because the larger the sample size is, the more we're expecting those averages to be closer and closer to each other. So that's another reason why we like to take large sample sizes, because the larger our sample size is, the better or more reliable our statistic is going to be, because we're not expecting a lot of variation if we have large sample sizes. Okay, so the example we just did, we were talking about a normal distribution. So those cans, the soda cans we were saying were normally distributed. But what's even more interesting is that even for original populations that are not normal, we're going to see that the sampling distribution will be normal as long as we take a large enough sample size. And so this is one of the most important rules that we talk about, especially in the second half of the semester, is the central limit theorem. And the central limit theorem says that for a relatively large sample size, our sample mean is going to be approximately normally distributed no matter what the original population looked like. So even if your original population was skewed to the left or binomial or uniform or whatever it looked like, as long as we take a large enough sample size, what we'll see is as we increase that sample size, we come down to where we're going to get a normal distribution in the sampling distribution. And so the magic number we use for this is 30. So, you might think, okay, well, if we have to have a large sample size, that's a big number, but really we're just talking about 30 or more. Okay, so for these problems, I'm going to go back to using the notes that already are filled in from last semester, just because it's easier and my writing does not look as good when I try to do it using this writing pad. So we're looking at a medical procedure that was modeled by an insurance company. It has a normal distribution with a mean of 775 and a standard deviation of 150. So the main thing we want to look for in these problems when we're trying to figure out, is this something like what we did in chapter 7 or is this more like chapter 8, is what are we trying to find the probability of? So this one says we want to know the probability of a randomly selected patient. Okay, so a randomly selected patient is one person. So we're just wanting to know what's the probability one person would be charged $800 or more. Now that is what we did in chapter 7. We looked at the distribution of all the different treatment costs, and we would look at what's the probability someone would be charged more or less or whatever, right? And so this one, our original population has a mean of 775, right? And a standard deviation of 150, and it told us it was normal. And so we're just trying to find this upper tail there, right? $800 or more. So because we're trying to find the area, we're going to use normal CDF from 800 up to infinity, which remember we use our 9999 number there for infinity, our mean and standard deviation that we're given, and we get 0.4338. So that is the probability that a single patient would be charged $800 or more. Now, something that we would do in this chapter is we start talking about the sampling distribution. And so it says, describe the sampling distribution of the sample mean for samples of size 15, right? So we have samples of 15. All right, so we need to know three things to be able to describe the sampling distribution. The first thing is we need to know, is this sampling distribution going to be normal? So the two ways that we can figure that out is either the original population is normal, which in this case it was, right? It told us that it was a normal distribution. So that's true for this one. So it is going to be normal. But if that's not the case, then you need a sample size of 30 or more. This one did not have a sample of 30 or more, but that's okay because the original population is normal. If your original population is normal, it doesn't matter what size sample you take. Every sampling distribution coming from a normal population will still be normal, no matter the sample size. So then we also need to know the mean, which we said will be equal to the mean of the original population. And the standard deviation will be equal to the original standard deviation divided by the square root of n, which of course we got from this here. We had a sample size of 15, so that's where the 15 came from. If we were taking samples of 80, we would divide by the square root of 80. Okay, so of course you could put that value in your calculator, the 150 divided by the square root of 15, but it's just going to be a long decimal. So for this one, I'm just kind of going to leave it as it is and use that for our standard deviation. So in part C, it says, what is the probability that a randomly selected group of 15 patients will be charged $800 or more for the treatment? So the difference in part C and part A is that part C is talking about a group of people. So instead of just looking at one patient, we're talking about 15 patients. Okay, so that means we do have a sample size, right? Which means we will be looking at the sampling distribution and not just the original population. So we actually already created the sampling distribution in part B for samples of size 15, right? We found the mean and the standard deviation here. So if we want to know this area, we're going to use our normal CDF. And basically all our numbers are going to be the same, but what's going to change is that, remember, our standard deviation, because it's in the sampling distribution, is equal to this value here, right? So that changes. Other than that, it looks pretty much like what we did in part A, right? And so this comes out to 0.2593. So it's less likely to get that higher value when you're looking at a group of people versus when you're just looking at one individual. Okay, and so we could also use the inverse norm or have a question where we would use inverse norm in the sampling distribution. So for D, it says if we're looking at random samples of 15, so that's just letting us know we are talking about the sampling distribution and not the original population. The highest 5% of groups are charged what? Okay, so this is what we're trying to find. We have an area of 5%, and we want to know what this value is here. And that value, typically we would call an X, but in this case, we're going to call it an X bar because we're in the sampling distribution. And in the sampling distribution, all the values are sample means. At least in this first section, we're talking about sample means. So we would use the inverse norm like we have before. The area to the left is 0.95. The mean of the sampling distribution is 775, and the standard deviation is the 150 over the square root of 15. And so for that one, we get the highest 5% of groups would be charged $838.70 or more. So this gives us an idea of what to look for in our problems to tell if we're going to be using the original population or if we're going to be using the sampling distribution. So if you're given a sample size or it's talking about an average or a sample mean, then those are some clues telling you that we are talking about the sampling distribution and not the original population. Okay, now this next one, to decide if this one group of pregnant patients are unusual compared to the population. Okay. And so because we're looking at a group of patients and we're not just saying, is this one patient unusual? We're looking at a sample of 35 patients, then we're going to be in the sampling distribution. Okay. So if we're going to use a sampling distribution, we need to know if it's normal, right? So would this be a normal distribution in the sampling distribution? And we would say yes, because we're taking 35 for our sample, and that is more than 30. So we will have a normal distribution in the sampling distribution. The mean comes from gave us from the population. It says the mean weight gained during pregnancy is 30 pounds with a standard deviation here of 12.9. Okay, so that's from the original population. So using that in addition to our sample size is how we would get our sample mean and then our sample standard deviation. So how would we know if it was unusual? This is something that we have talked about throughout our time together in several different ways, looking at if something was unusual or if it was an outlier. And so how we're going to do that in this chapter is we are going to look at, well, what's the chance of that happening, right? So let's say we have a sample of 35 and they have an average weight of 36.2, right? Now, how likely or unlikely is that to happen? The way we're going to do that is find the area, right? And so remember, the area is what tells us the probability or the percentage of the group that fall into that space, right? So to find the area, we're going to use normal CDF using the information we just used here, or we just found here. And then, of course, we're going from 36.2 up to infinity. And this tells us the probability of getting a sample of 35 that had a sample mean of 36.2 or more. And so this is very, very unlikely to happen, right? This is something that would happen less than 1% of the time. Okay, so if we're trying to decide if this group is unusual, what would we say? Is it unusual? Yes, right? This would be very unusual to happen because it falls so far from the mean or where we would expect it to be. And so it does look like this group is gaining more than average. It looks like something is unusual about the group. And so then we could take this information back to the doctor and they could decide, maybe they have some theories as to why that is happening. Maybe they find that low-income patients maybe have their diet isn't as healthy, or maybe they're not taking the right vitamins, or maybe they have some condition that makes them more likely to gain weight. Whatever reason, we don't really know what that is. We just know that this group of 35 has a very unusual average weight gain, okay? And so that is kind of what this is telling us. And that's what we're going to be working towards in chapter 9 and 10 is if we are trying to investigate something and figure out, hey, is this new drug really a good thing? Or, hey, did vitamin D help people when they were diagnosed with COVID-19, or, whatever we're trying to look at? We want to be able to identify what the chance is of that happening in the population we were expecting. Okay, so how likely or unlikely is it that that would happen? So since this is very unlikely to happen, we would say it would be an unusual event. And so there is something different about that group. Okay, and then we have one other example here, doing more examples, looking at the difference between if we're talking about just one car in this case, or if we're looking at a group of cars. So in the first example, it says a randomly selected cobalt, so one car. The second one says we're looking at 10 cars, right? So we have a sample of 10. So the first one, we're looking at the original population. The second one, we are looking at the sampling distribution. Okay, so you could kind of read through those and see the difference, so you can start identifying that in your homework problems, especially on like your test, because of course the test will have some chapter 7 problems and some chapter 8 problems, so you want to make sure you're able to distinguish between the two. Okay, so what we have next for this chapter is looking at the distribution of the sample proportion, okay? And so sample proportions are when we are looking at percentages instead of averages. But because I've already spent 40 minutes on this lecture video, I will probably save that for another one. But the concept is going to be the same. We're just going to be working with percentages instead of sample means. All right. So look for that next video if you need some help on the sample proportion part. And please feel free to email me at angela.galloway@kctcs.edu if you have any questions over Chapter 8. Thanks.